We'll talk about inference of resource management specs.
Okay, hi everyone. This is work that was primarily done by the first two authors, Narges Shadab, my PhD student, and Pritam Gharat, a postdoc at Microsoft Research in India. I'm giving this talk due to many unfortunate visa issues, but Pritam, the second author, was the one who prepared these slides, and I believe she's on the job market this year. Okay, so today I'm going to cover the following. I'll give a quick overview of some recent work we've done on a resource leak checker that works for both Java and C#, and it's kind of different than other tools in the space in that it's based on these resource management specifications at method and class boundaries, so we get some very nice properties from that. Then I'm going to talk about the main focus of this work, which was on inference of these resource management specifications. I'm going to talk a little bit about our experimental evaluation and finally conclude. And I'll note many times in the talk and now that there's not going to be a lot of the technical details here. I really encourage you to read the paper to find out the full story on this work. So let me start with the overview. So what is a resource leak? Well, in Java and C#, we're talking about resources. We mean kind of finite resources in the system that you have to manage explicitly. So we're not talking about memory that is garbage collected. We're talking about things like file handles and network sockets, resources where you have to explicitly release them, say in Java by closing a file handle. So a resource leak occurs when a programmer fails to explicitly close this finite resource. And this can lead to a lot of problems, right? Resource starvations, system slowdowns, crashes, and it's really quite a bad problem because it's hard to test for. Often this manifests only when you've deployed into production and run for a week and all of a sudden things are going slower and you're not sure why. So it would be great if we could effectively statically detect these types of problems. So in recent work that was published in FSE 2021, we developed a resource leak checker, a pluggable types approach to finding resource leaks. In that work, we implemented this in the checker framework for Java, and subsequently it was implemented for C#. The resource leak checker uses a lightweight and modular and sound approach to preventing resource leaks. And the kind of cool thing here is that you can detect resource leaks without doing whole program alias analysis. So that's what makes it lightweight. But we do need these resource management specifications to understand how responsibility is being shared across method boundaries, and also in certain cases, what kinds of aliases are arising that are relevant here. So these specifications are great because they let us do incremental and modular checking very easily, and they improve the quality of the warnings that we can give in this checker. But someone has to write these annotations. We did it for the previous study, and we found that particularly for large legacy code bases, it was a lot of work, right? So this work that I'm talking about today was motivated by reducing the overhead for developers of manually adding these annotations. And with this inference system, now you can run this resource leak checker in a fully automated fashion. You can run it on an unannotated code base and get fairly useful results out of it. So after I tell you more details about the system, I'm going to show you some of our results where we compared between handwritten specifications and the specifications we're able to infer, and also just seeing how well does the resource leak checker run out of the box if we combine it with inference but don't do any manual annotation ourselves. So let me illustrate what's going on with this checker with a small example. So this is a code snippet, and it's actually fine. There's no resource leak in this code snippet, and the resource is up here. It's this SQL connection that needs to be closed. So let's see what's going on and why this code is free of leaks. So as I mentioned, our checker relies on some form of annotations to understand which alias is going to be responsible for closing a resource. And the annotation I'm going to focus on in this talk is one we call owning. Now we've heard lots of great talks about ownership. I want to distinguish our notion of owning from the much stronger notions that you see in a language like Rust. Here what we have is something we call lightweight ownership, and it's basically just a hint to our checker as to which alias is going to be responsible for closing this resource, but it does not restrict in any way how you can create aliases in your program. So here, and this is using a C# syntax for annotations with the square brackets. Here, the owning on the declaration of getSQL connection says that whoever calls this getSQL connection method is responsible for closing the returned resource. And down here in close connection, the annotation says, if you pass me a connection, this method will take responsibility for closing it. Okay? So those are the annotations. And based on this, we can see that this example is safe, right? This method creates a SQL connection, but it's going to transfer the obligation for closing it to the caller. And then this caller right here is able to satisfy that obligation by calling close connection. And we know that that works because we see this annotation on the parameter, and we can separately verify this method on its own that it takes care of that obligation to close the resource. So the other nice thing about having these annotations is compared to other systems, we can kind of give errors in more appropriate places. And in this example, the fact that we have this owning annotation here means we won't warn inside this method that you didn't close the connection. And you may think, well, of course you need something like this, but there actually are pretty common heuristic checkers out there for Java that don't even do this. And so they give you a lot of noise in the reports. But here, let's say you deleted line 11, we would be able to give you the error at this program point and say that here's the connection and this method is responsible for closing it and didn't do anything about it. And there are many other types of annotations that I'm not going to get into detail, but they're very important. I encourage you to see the paper for more details on these. But we have annotations for wrapper types. So if you're storing a resource in a final field, we can support that. We can support aliasing between different objects that manage the same resource. And this is all critical for effectiveness in practice. Okay, so as I mentioned, annotating legacy code to work with our checker is a hindrance for adoption. We have our own personal experience here where we looked at some fairly sophisticated Java programs like Zookeeper and Apache Hadoop. And we spent several weeks trying to puzzle through the protocols and annotate a moderately sized program. And in the end, to be honest, we kind of gave up. And we said, we can't figure out everything that's going on in this program. What we're going to do is try to add annotations when they're using resource types in standard libraries. But if they have their own wrapper types, we threw up our hands and said, we're not going to try to figure this out. And so, given that we were highly motivated to do this, I'm not sure a developer who we're trying to convince to use our tool will be very convincible. So that's the main motivation behind this inference technique. So let me talk next about what's interesting at a high level about our inference technique. So this is not a straightforward problem because these resource management specifications have to capture multiple interrelated properties. So which alias is responsible for closing a resource? What are the obligations that need to be satisfied on different types? And when do we have aliases where it's fine to close a resource via either one of them? So we needed an inference. These are all interrelated. We needed an inference technique that could kind of simultaneously infer all these types of annotations. Another thing, the second bullet is key here, is that we found that we wanted to employ an optimistic approach to inference. So perhaps unsurprisingly, very often when you're applying our checker to an unannotated legacy code base, there are bugs. Right? So we're never going to be able to find a set of annotations that makes it past the checker. So the question is, where should we put the annotations? And we tried to do it in a way that matched what appeared to be the developer's intentions. And that helps a lot because then even though it doesn't pass the checker, you get error messages in more appropriate places than if you were very strict and only inferring annotations that would be verified. So in the paper, you can see how we formalize the inference algorithm as a set of inference rules. It's using a data log style syntax, and then inference can be viewed as just applying those rules to a fixed point. And we have two different implementations of this. As I mentioned before, we implement inference for both Java, based on the checker framework, and in CodeQL for C# code bases. So what I'm going to do here, rather than going through all the rules, is trying to illustrate some properties with a single example. So why this optimistic approach is useful, and then I'll show you one of the rules and how it works. So here's our example. It's a cleanup method that takes in a socket, and then what it does is it does some shutdown routine to disable operations on that socket, and then it closes it. And the problem here is that while it seems clear that this method was intended to always close this socket, it may not do so, because this shutdown routine called on line 3 might throw an exception. And if that happens, then close will never be called, right? So if you took a more standard approach to inference, you would try to focus on what can we infer about this method that is true of the code that's there right now. And if we stuck to that approach, we would not infer any annotations for this method, because we would say, hey, it might not actually close that socket, so we better not put in an annotation there because that's not going to be verified. But this is actually not the right thing to do for this code. Maybe intuitively, it seems when reading this code that there was an intent here to always close this socket. And if we don't infer an annotation there, what that leads to is confusing error messages for the developer elsewhere in the code, right? Maybe cleanup is called in 10 different places, and the checker will treat that operation as if it's not doing any cleanup at all. So you'll get 10 different error messages at all those call sites, rather than a single error here in this method where the real problem is. So the optimistic approach aims to mirror the developer's intent. So here we infer an owning annotation on this socket parameter, and that's going to lead to an error, but it'll lead to an error in this method, which typically is the right place to fix this. So let me show you the rule that infers this owning annotation quickly. So, and you can see all the rules in the paper. It's of a data log style, like I mentioned. So here we see that the type of this parameter is T, it's a socket, and we have built-in models of the standard libraries that says there's an obligation on sockets, you have to close them. And here's the interesting part, we check whether there exists a call to close in this method, right? So we don't check that it happens on all paths. We say if there exists a call to close, we're going to infer this annotation because in our experience, it's very rare for a method to conditionally close a socket and then sometimes leave the responsibility for somebody else. So as I mentioned, there's many more rules in the paper. Please go see the paper for more details. Okay, let me briefly cover some results from our empirical evaluation. So the first experiment that we did was we had done handwritten specifications beforehand for several benchmarks. So the top 5 benchmarks here are C# code bases, and the bottom 3 are Java code bases. So we wanted to run our inference and see, can it infer the annotations that we wrote by hand? And we had pretty good results, I think. 82% recovery rate in open source C# projects. That's these two. 74% in open source Java projects. And actually for the proprietary C# microservices that we looked at, we were able to uncover 100% of the handwritten annotations. We don't have a proved explanation for this. We suspect that that code was under more rigorous code review and maybe structured more in a way that's more amenable to this kind of checking. In terms of why we missed annotations, they were reasons that were, in my opinion, kind of weird code. Like there were classes where there were multiple different methods that might release the resources that were public, and we picked the wrong one. So that we missed the right annotation there. There were places with an abstract class that had fields, and subclasses were managing the closing of those fields. We don't have techniques for supporting that right now. So that explains roughly the reasons we missed annotations. The next thing we did, as I mentioned before, was let's see what happens when we take an unannotated code base, run inference, and then run the checker on the result. So first we compared the number of warnings that we saw. NS is no specifications, so just running the checker, and this is with inferred specifications. And you'll notice that the number of warnings actually goes up in many cases. And I want to argue this is actually a good thing. This is because our inference is discovering new obligations that actually need to be checked. And so it's again giving you errors in the right place. So for example here, with my original example, it will give you an error in the right place due to the inference. Finally, I wanted to talk about the warnings. We triaged a sample of the warnings and tried to look at what was going on. So the true positive rate here is 28% for C#, 19% for Java. And this may not look very high, but it's very close to what we saw in previous work. And without getting into details, if you look at most tools out there, they don't do much better than this. The percentage of incorrect specifications was quite low. And finally, there were some missing specifications. I'm happy to talk more about this, but there were some common cases, non-resource types in C#, and mutable fields in Java. I don't know, we need some help. I'm happy, please come help me. We're trying to figure out how to handle these better. We don't have a good way to specify how they're doing, so we don't do well. So that's what I had today. I just wanted to show you that if you look at our manual annotations, we got lower quality warnings because we didn't have the energy to actually go through and annotate everything. But if you look at the inferred annotations, we actually got better warnings in the right places, and we're actually able to detect some new bugs in these benchmarks that even after the manual annotation before, we couldn't find them. So that's it. These are our contributions, and everything is open source. So I encourage you to go and check out the resource leak checker for either of these languages and the inference. Thank you very much.
Okay, if we have any questions, please come to the aisles quickly.
Hey, so this is super cool, and I'm wondering, what would you say is sort of the key insight in being able to go from sort of like the formal calculus to how do you relax things for inference, right? Because in some sense you're taking a step back from sort of like the traditional inference approaches to sort of capture developer intent. What's like the big step that's maybe like a step removed from just resources?
That's a good question. I don't immediately know how I can generalize this. I mean, for our case, it was, if you look at the rules in various places where you would check that something always happened, it was taking a for all to a there exists. But I don't immediately know for other properties or other type systems how that would generalize. I'd love to brainstorm about it more.
All right, cool. Yeah, I mean, that was kind of the answer I was wondering about, so.
Okay, thanks.
Do we have time for another question or no?
Very quickly.
We can take it offline, thanks.
Okay, let's thank Manu again.